Galvanic corrosion of carbon and steel in aggressive environments. Galvanic corrosion refers to the electrochemical process when electrons can freely move between two different materials. The material with the lower electrical potential, which is more negatively charged, serves as the anode, and the substance with the higher electrical potential, which is more positively charged, serves as the cathode. The anode loses electrons to the cathode and releases positive ions into the electrolyte when the two materials are linked. Figure 1 shows the galvanic corrosion cell. Carbon fiber reinforced plastic, CFRP, laminates have been used in strengthening of reinforced concrete and steel beams. This is due to the high modulus of the composite, which will enable the steel beams to endure higher load applied. However, due to close contact between carbon fiber from CFRP and the steel in the presence of electrolyte, galvanic corrosion could take place and cause subsequent delamination or debonding. In this case study, corrosion rates of samples with different thicknesses of epoxy coating in different electrolytes provides a thorough understanding of the phenomenon and assists in developing techniques to eliminate the galvanic corrosion problem. Here is the list of materials. All electrochemical measurements were performed on an EG&G Princeton Applied Research 273A potentiostat. The complete setup is shown in Figure 3. Both potentiodynamic polarization tests and galvanic corrosion tests were carried out in a flat cell made from perfluoroalkoxy as shown in Figure 4. The cell had a volume of 100 milliliters with 3 openings that could be used for different electrodes. A standard O-ring was used to seal the specimens to the side openings while exposing exactly 100 square meters area of the specimen to the electrolyte. In polarization tests, the working electrode was specimen either steel or CFRP, platinum plate acts as the counter electrode and SCE acts as the reference electrode. In the galvanic corrosion test, a steel coupon served as the working electrode, whereas the counter electrode was a carbon specimen and SCE acts as the reference electrode. 4 polarization tests were conducted on steel in their original form and carbon fiber specimens coated with a thin epoxy film. They were tested and immersed in seawater and de-icing salt solution with different salt concentration and pH value. Tafel slopes were determined from the polarization diagrams to evaluate corrosion current density and corrosion potential. The steel specimen in the de-icing salt solution showed minor signs of passivation, indicating temporary protection from further corrosion. The corrosion rate is determined by the corrosion current density obtained from the diagrams, according to Faraday's law. In both solutions, the cathodic reaction for steel and carbon specimens was the reduction of oxygen in the formation of hydroxide ions, O, on the surfaces. Carbon specimens had higher corrosion potentials than steel, indicating carbon's greater nobility in both electrolytes. The corrosion current densities of carbon fiber reinforced polymer, CFRP, were higher than those of steel in both solutions, suggesting that steel corrodes faster when coupled with carbon in these solutions. When steel was coupled with carbon, it corroded approximately 13.7 and 13.4 times faster in the de-icing salt solution and seawater, respectively, compared to when carbon was absent. This estimation was based on the intersection of the polarization plots on the Evans diagram. Thank you for watching.